Our universe might be 10 times more complex than we ever imagined. A leading astrophysicist recently suggested our most successful models of the cosmos are fundamentally incomplete. By the end of this journey, you will see the fundamental building blocks of reality in a completely new light. We will explore why stars move as if pulled by invisible hands and what force is tearing space itself apart. Are you ready to question what you think is real? For decades, our best maps of the cosmos have been built on two powerful pillars. The first is the Standard Model of Particle Physics, a breathtakingly precise theory that describes the fundamental particles and forces that make up everything we can see and touch. The second is the Lambda CDM model, our leading picture of the universe's overall evolution, from the Big Bang to the vast cosmic web we observe today. These frameworks are monuments to human ingenuity. They correctly predicted the faint afterglow of the Big Bang, known as the cosmic microwave background, and they accurately forecast the cosmic abundance of the lightest elements, like hydrogen and helium. Yet for all their success, these models are fundamentally incomplete. They are like a detailed street map of a single city that shows nothing of the immense, uncharted wilderness surrounding it. This is because our maps fail to account for dark matter and dark energy, two mysterious components that together make up over 95% of everything that exists. The matter we understand, the stars and planets and you and me, is just a tiny fraction, a mere 5% of the cosmic whole. The very precision of our models for this small, visible sliver of the universe can make us overconfident, potentially blinding us to the vast and unknown physics governing the overwhelming majority of reality that remains hidden in plain sight. The first great mystery is like watching the wake of a giant ship cut across a still ocean, a powerful, churning trail clearly visible, yet the vessel itself remains completely unseen. This is the essence of our search for dark matter. We see its gravitational wake everywhere. It dictates how galaxies spin at speeds that should tear them apart, and it sculpts the immense cosmic web, the filamentary structure upon which all visible matter is draped. The pioneering astronomer Vera Rubin provided some of the most compelling evidence for this invisible hand. By meticulously measuring the rotation of galaxies, she found stars at the outer edges moving just as fast as those near the center. According to the laws of gravity, these far-out stars should be flung into the void, like a child spun too fast on a merry-go-round. The only explanation was that the galaxies were embedded within vast, heavy halos of something we cannot see, a substance that does not emit, absorb, or reflect any light. This dark matter is the universe's ghost, a cosmic scaffold that holds the glittering cities of stars together. Its existence is a direct and profound challenge to the Standard Model of Particle Physics. That model describes a universe built from particles that interact with light and with each other through known forces. Dark matter, by contrast, seems to be utterly aloof. It passes through our planet, our homes, and our bodies as if we were not even there, interacting only through the whisper of gravity. This has led physicists on a decades-long hunt for what it could possibly be. The leading candidates have names like WIMP, or weakly interacting massive particles, and actions, hypothetical particles so light and numerous they could permeate every corner of space. Countless experiments housed deep underground to shield them from cosmic interference are listening for the faintest tick of a dark matter particle. Yet so far the silence is deafening. This persistent failure to find a single candidate forces us to ask a more radical question. What if dark matter is not one solitary particle, but the tip of an entire hidden iceberg? What if it constitutes a complete shadow universe with its own zoo of particles and its own fundamental forces, all operating in parallel to our own, completely undetectable by any means we currently possess. This single idea would instantly multiply the complexity of our cosmos, and it leads us directly to an even more bizarre and dominant force, one that is not just hidden, but actively pushing the universe apart. If dark matter is the universe's invisible scaffold, then dark energy is its ghost in the machine, an unseen engine whose pressure on the very fabric of space is accelerating the cosmos apart. This second mystery is even more baffling than the first. While dark matter pulls with gravity, dark energy appears to push, and its influence is not fading. It grows stronger as the universe expands, stretching the void between galaxies at an ever-increasing rate. This startling discovery, made in the late 1990s by teams studying distant supernova, earned a Nobel Prize and turned cosmology on its head. The universe was not just expanding, it was in a runaway acceleration. As cosmologist Michael Turner, the scientist who gave this force its name, once said, "It is the most profound mystery in all of science." To explain it, physicists have returned to an old idea from Einstein himself. He called it the cosmological constant, a mathematical fix he added to his equations to represent a repulsive energy inherent to empty space. He later called it his greatest blunder, but it seems he may have been right for the wrong reason. This constant is now the leading candidate for dark energy, a uniform energy density woven into the vacuum of spacetime. Yet here we encounter a problem of staggering proportions, a discrepancy so vast it is the worst theoretical prediction in the history of physics. Our best quantum theories predict a value for this vacuum energy that is over 120 orders of magnitude too large. That is a number with over 120 zeros after it. If the theory were correct, the repulsive force would have been so immense that it would have ripped apart stars, planets, and even atoms before they could ever form. The universe as we know it would not exist. So why is the observed value of dark energy so infinitesimally small, yet not quite zero? This colossal failure of our models points to a fundamental gap in our understanding. What if dark energy is not a simple, unchanging constant after all? Could it be a dynamic field, one that evolves over cosmic time, interacting with dark matter or other hidden components in ways we cannot yet fathom? This single possibility opens a door to a cosmos of unimaginable complexity, where the very vacuum of space is alive with change. Even the most powerful telescopes in existence are staring into a past we can never fully access. We see the light from distant galaxies as they were billions of years ago, but this creates a fundamental boundary, a cosmic horizon. Beyond this horizon, light has simply not had enough time to travel to us since the universe began. What we call the observable universe, with its hundreds of billions of galaxies, is not the entirety of existence. It is merely our local cosmic neighborhood, the small patch of a vast forest illuminated by our own tiny campfire. The rest, the overwhelming majority of the cosmos, lies in permanent shadow forever beyond our view. This is not a limit of our technology, but a limit imposed by the finite speed of light and the age of the universe itself. We are, in a very real sense, trapped on a cosmic island. This profound isolation forces a startling question. What lies beyond the horizon? The leading theory of the universe's birth, cosmic inflation, provides a mind-bending answer. It suggests that in the first fleeting fraction of a second, space itself expanded at an exponential rate, far faster than the speed of light. This inflationary surge did not just create our one universe. It may have seeded an infinite multiverse, a frothing ocean of bubble universes, each with its own unique laws of physics. In this staggering picture, our entire observable cosmos, with all its galaxies, stars, and planets, is just a single bubble in an infinite cosmic foam. Some of these bubbles might have stronger gravity, making planets and life impossible. Others might have different fundamental particles or no dark matter at all. Some might collapse instantly, while others expand forever. If this theory holds, then the true scale of reality is not just 10 times more complex than we imagined. It is effectively infinite, an endless tapestry of realities where every possible variation of physical law plays out somewhere. Our known universe, for all its splendor, would be reduced to a single, possibly unremarkable, data point in an incalculable vastness. A cat is both alive and dead inside a sealed box. This is not a description of some macabre magic trick, but the core of a famous thought experiment designed to expose the profound strangeness of the quantum world. Erwin Schrödinger conceived this paradox to illustrate a concept called superposition, where a particle like an electron can exist in multiple states or locations at once until the moment it is measured. This leads us directly to the third great mystery, the quantum measurement problem. It is the unresolved question of why the mere act of observation forces a fuzzy cloud of possibilities to snap into a single, definite reality. The physicist John Wheeler took this idea to its ultimate conclusion, proposing that we live in a participatory universe. In his view, reality is not a pre-recorded movie that we passively watch. It is more like a cosmic game of 20 questions where the very act of asking a question, of making an observation, brings the universe into being. The past, he suggested, is not fixed. It is shaped by the questions we ask in the present. This is not just philosophy. It is a genuine scientific puzzle with competing explanations, each more mind-bending than the last. The traditional view, known as the Copenhagen interpretation, states that the wave of probability simply collapses upon measurement, but it refuses to define what truly constitutes an observation. Is it a conscious mind, a machine? This vagueness has prompted other theories. The many worlds interpretation offers a radical alternative, suggesting that the wave never collapses at all. Instead, every possible outcome of a quantum event actually happens, but in a newly branched off parallel universe. In this view, there is a universe where the cat lives, and another, equally real universe where it dies, and the act of opening the box merely determines which branch you find yourself in. Then there are objective collapse theories, which propose that superposition has a natural lifetime and breaks down on its own when a system becomes too large or complex. Each of these interpretations attempts to solve the same fundamental puzzle, yet they paint wildly different pictures of reality. So what does this quantum weirdness mean for our understanding of the cosmos? Could the very act of measurement be a gateway, a process that taps into a deeper layer of cosmic information processing that we are only beginning to glimpse? If observation does play a role in shaping reality, then the universe is not just a cold, mechanical clockwork. It is an interactive system, and our place within it may be far more active and mysterious than we ever dreamed. Even the seemingly smooth fabric of spacetime, the very stage upon which the cosmic drama unfolds, might be an illusion. General relativity paints a beautiful picture of a continuous, pliable fabric, warped by planets and stars to create the force we call gravity. Yet this elegant theory breaks down at the center of black holes and at the moment of the Big Bang, points of infinite density where the mathematics simply fail. This failure hints that our understanding of space and time is fundamentally incomplete. What if the smooth continuum is not the final answer? What if space-time itself is not fundamental, but emerges from something deeper, just as the sensation of temperature emerges from the collective, frantic motion of trillions of individual molecules? This is the radical proposal at the heart of our most ambitious theories of quantum gravity. Two leading contenders, loop quantum gravity and string theory, take this idea in different yet equally astonishing directions. Loop quantum gravity suggests that space is not infinitely divisible. Instead, it is woven from a fabric of tiny, discrete loops, a network of intersecting threads a billion trillion times smaller than an atomic nucleus. In this view, the very geometry of space is quantized, meaning it comes in tiny, indivisible packets. Picture the pixels on your screen. From a distance, the image appears smooth and continuous, but zoom in close enough and you see the individual blocks of color that compose it. Loop quantum gravity proposes that reality itself is pixelated at this unimaginably small scale. String theory offers another layer of hidden complexity. It posits that the fundamental constituents of reality are not point-like particles, but incredibly tiny, vibrating loops of energy. The different vibrational patterns of these strings give rise to all the particles and forces we observe, from electrons to photons. Crucially, in string theory, the dimensions of spacetime are not the fixed four we experience. The theory requires extra compactified dimensions, curled up so small that we cannot perceive them. In this framework, every single point in our familiar four-dimensional spacetime contains a hidden, intricate geometric shape governing the possible vibrations of the strings. So the vacuum of space is not truly empty. It is a seething ocean of quantum potential, a dynamic, multi-layered entity built from a near-infinite number of these vibrating threads and geometric knots. If this is true, then the universe is not a simple, passive stage. It is a computational network, a constantly evolving tapestry of information and energy whose true, granular nature remains forever hidden from our blunt, macroscopic instruments. This realization forces a profound shift in perspective, suggesting that our foundational tools for exploring the cosmos might be fundamentally limited, built to perceive only the emergent shadows of a deeper, far more complex reality. Our own existence is the most compelling clue to the fourth great cosmic mystery. We live in a universe made almost entirely of matter. The screen you are looking at, the planet beneath your feet, and the stars above are all built from it. But according to our best theories, this should not be. The Big Bang should have created equal amounts of matter and its mirror opposite, antimatter. When a particle of matter meets its antimatter twin, they annihilate each other in a flash of pure energy. If the early cosmos had been perfectly balanced, all of its contents should have mutually destroyed one another, leaving behind a desolate, expanding sea of radiation. There would be no galaxies, no planets, and no one to wonder why. The simple, staggering fact that we are here means the initial symmetry was broken. This is the Baryon asymmetry problem, the profound puzzle of why matter prevailed. The physicist Andrei Sakharov identified the three essential ingredients needed to create our matter-dominated world from an initially symmetrical state. First, there must be a process that violates Baryon number. This is a conservation law stating that the total number of heavy particles like protons and neutrons cannot be created or destroyed. To generate an excess of matter, this rule had to be broken. Second, the universe had to violate both charge conjugation symmetry, which means the laws of physics must treat particles and antiparticles differently, and charge parity symmetry, a more subtle combination of mirroring particles and flipping their spatial coordinates. Essentially, the cosmos needed a built-in preference for matter over antimatter. Third, these processes had to occur out of thermal equilibrium, away from the smooth, hot soup of the early universe, to prevent the emerging imbalance from being immediately wiped out. Experiments have indeed found tiny violations of these symmetries. we have observed certain rare particle decays that treat matter and antimatter slightly differently. But the effect is far too small, a mere 1 part in a billion, nowhere near enough to account for the overwhelming abundance of matter we see today. So what tipped the scales so dramatically? Could there have been unknown, heavy particles in the primordial furnace that decayed, favoring the production of matter by just enough to leave behind the raw material for everything we see? Or perhaps a fundamental force we have not yet discovered briefly influenced the newborn cosmos, imprinting it with a preference for existence over annihilation. This puzzle suggests that the initial conditions of our universe were not simple and symmetric, but were shaped by a far more complex and dynamic set of physical laws than our current models can describe. This single, crucial moment of asymmetry leads us back to the very beginning, to the event that may have set the entire cosmic stage. Cosmic inflation is the grand prologue to our universe's story, a fleeting instant of unimaginable expansion that solved several profound puzzles at once. Before this inflationary burst, the cosmos was a chaotic, seething quantum foam. Then, driven by a hypothetical field known as the Inflaton, space itself underwent a staggering exponential expansion, doubling in size over and over again in a fraction of a second. This explosive growth stretched a tiny, primordial patch of space into a volume far larger than our entire observable universe, ironing out any wrinkles and leaving it remarkably flat and uniform, just as we observe in the cosmic microwave background. But inflation did more than just smooth the cosmos. It also amplified the faintest quantum jitters, the inherent uncertainty of the Inflaton field itself. These microscopic fluctuations were stretched to astronomical sizes, becoming the seeds of all future structure. The slightly denser regions in this primordial imprint began to pull in more matter through gravity, eventually growing into the vast cosmic web of galaxies, clusters, and superclusters we see today. Every galaxy, including our own Milky Way, owes its existence to these quantum seeds planted during inflation. Yet for all its explanatory power, the Inflaton field remains a complete mystery. We do not know what it is, what kind of particle it represents, or what laws governed its behavior. It is a placeholder in our equations, a theoretical necessity whose true nature is completely hidden from us. This uncertainty opens the door to a staggering array of possibilities. Different models of the Inflaton field predict wildly different outcomes for the universe. Some lead to a clean, one-time inflation that produced our single, orderly cosmos, but other models suggest a far more dramatic and eternal process. In these scenarios, once inflation starts, it never truly stops. It continues eternally, spawning an endless froth of bubble universes, each one pinching off from the inflating background with its own local laws of physics. Our entire universe in this picture is just one bubble in an infinite cosmic foam. In some of these bubbles, the strength of gravity might be 1,000 times stronger, instantly crushing any possibility of planets forming. In others, the nuclear forces might be too weak to bind protons and neutrons, leaving no atoms, no chemistry, and no life. The fundamental constants we take for granted, like the mass of an electron or the charge of a proton, could be mere local ordinances, valid only in our own cosmic neighborhood. The mechanism that created our familiar, life-giving cosmos might, by its very nature, also generate an infinite diversity of other realities, most of which would be utterly alien and uninhabitable. This single idea transforms our search for a theory of everything. We are no longer just trying to explain the one universe we see. We may be attempting to map the laws of a single island in an endless, unknowable archipelago. Finding a single, perfectly tuned radio station amidst a sea of overwhelming static would feel like a miracle. This is precisely the kind of miracle we encounter in the heart of particle physics, a puzzle so profound it challenges our core assumptions about nature's elegance. This is the hierarchy problem, and it revolves around the most famous particle of the 21st century, the Higgs boson. The mystery is not its existence, but its astonishingly low mass. According to our theories, the Higgs field gives mass to other particles by interacting with them. But what gives the Higgs itself its mass? The natural anchor for this mass should be the Planck scale, the incredibly high energy level at which gravity becomes as strong as the other fundamental forces. At this scale, the Higgs should be unimaginably heavy, about 1,000,000 billion times heavier than it actually is. Why is it so impossibly light? As Nobel laureate Frank Wilczek has articulated, this creates a deep naturalness problem in fundamental physics. Nature, left to its own devices, does not seem to favor such exquisitely fine-tuned numbers without a reason. The core of the problem lies in the quantum world. The Higgs mass is not a static number. It is constantly being jostled and corrected by a storm of virtual particles flickering in and out of existence. Every known particle, and potentially every unknown one, contributes to this quantum jitter. These corrections should drive the Higgs mass to the highest possible energy, up to the Planck scale, like a dial being spun wildly by invisible hands. For the observed mass to remain so small, there must be an almost perfect cancellation occurring. The contributions from different particles must balance each other out with a precision of 1 part in 1,000,000 billion, a cancellation so precise it seems absurd to call it a coincidence. For decades, the most elegant proposed solution was a principle known as supersymmetry. This beautiful theory posits that every known particle has a hidden, super-heavy partner. The magic of supersymmetry is that the quantum contributions from these partner particles would naturally and exactly cancel out the corrections from their standard counterparts, effortlessly stabilizing the Higgs mass at a low value. It was a perfect theoretical fix, one that promised to solve the hierarchy problem and unite the forces of nature. But then, we built the most powerful machine in history to look for these superpartners. The Large Hadron Collider has probed energies where these particles should have been abundantly produced. The result was not the expected symphony of new physics, but a deafening silence. No supersymmetric particles were found. Their absence has deepened the mystery to a crisis point. The delicate balance we observe now appears to be just that, a balance. A fragile, seemingly unnatural fine-tuning with no clear mechanism behind it. This leaves us staring into a profound abyss. Is our understanding of mass and symmetry breaking fundamentally wrong? Or does this incredible fine-tuning point to something even more radical? Perhaps the value of the Higgs mass is not determined by elegant mathematics alone. It could be an environmental accident, one outcome among countless others in a vast multiverse. In most of those universes, the Higgs is heavy and atoms cannot form. We simply exist in the rare bubble where the numbers lined up just right for stars, planets, and life to emerge. The hierarchy problem, therefore, is more than a technical issue. It is a direct challenge, forcing us to question whether the universe is inherently natural and elegant, or whether the order we cherish is a fragile, statistical fluke in an immeasurably vast and chaotic cosmic landscape. The quietest objects in the universe hold the loudest paradox. A black hole's event horizon is a point of no return, a one-way membrane where the known laws of physics seem to break down. According to Einstein's theory of general relativity, anything that crosses this threshold is lost forever, crushed into the central singularity. The black hole remembers only the total mass, electric charge, and spin of whatever fell in. All the intricate details, the specific arrangement of atoms that made up a star, a planet, or a book, are utterly erased. This presents a direct and violent conflict with the bedrock principle of quantum mechanics, which states that information can never be truly destroyed. It can be scrambled, hidden, or made incredibly difficult to read, but it must, in principle, be recoverable. This is the information paradox, a fundamental clash between our two most successful descriptions of nature. The conflict was ignited by Stephen Hawking. He demonstrated that black holes are not completely black. Due to quantum effects near the event horizon, they slowly radiate energy, a faint glow now known as Hawking radiation. This process causes the black hole to evaporate, shrinking over astronomical timescales until it potentially vanishes entirely. Hawking's initial calculations suggested that this radiation was purely thermal, a random hiss of heat carrying no information about what fell in. If the black hole evaporates away, leaving only this featureless radiation, then the information about the original star and everything else it consumed is lost forever, violating quantum law. Hawking famously bet against information preservation, convinced his math was correct, but decades later, after a long and profound rethink, he changed his mind. He conceded that information must escape, declaring that he had found a mechanism for it to do so, and even paid out his bet. The question remained, how? How can information get out if nothing can escape? One of the most radical answers comes from the holographic principle. This idea suggests that all the information describing the three-dimensional volume inside a region of space, including everything within a black hole, is actually encoded on its two-dimensional boundary, the event horizon. Think of a credit card's hologram. A flat, two-dimensional surface stores all the information needed to project a seemingly three-dimensional image. In the same way, our perception of a rich, three-dimensional world, from the trees outside to the stars above, might be a projection from a vast, complex database of quantum bits living on a distant, two-dimensional surface we can never see. For a black hole, this means the information about every book, every atom, and every memory that ever fell in is not lost inside. It is smeared and stored like a cosmic pixel across the event horizon surface, and it is slowly and chaotically released back into the universe through the Hawking radiation. This is not just a clever fix for a black hole puzzle. If the holographic principle is true, it redefines the nature of reality itself. The universe is not fundamentally three-dimensional. The true, fundamental degrees of freedom, the ultimate code of the cosmos, exist on a thin, vibrating shell at the edge of our perception. The depth, the texture, the very feeling of space that surrounds you is an emergent illusion, a magnificent and convincing projection from a lower dimensional reality. This implies that the universe's ultimate complexity is not measured by its vast volume, but by the immense information processing happening at its boundaries, a concept that shatters our intuitive understanding of what is real. Vast magnetic fields weave through the cosmos like invisible threads, stitching galaxies and galaxy clusters into a single, coherent structure. These forces are powerful enough to guide cosmic rays and shape the birth of new stars, yet their origin is one of the most enduring puzzles in modern astrophysics. As the astrophysicist Ethan Siegel has pointed out, explaining how these immense magnetic fields arose is profoundly challenging. The leading explanation is a process known as the dynamo effect. Picture a simple bicycle dynamo where the spinning of a wheel generates an electric current, which in turn creates a magnetic field. On a cosmic scale, turbulent motions within the conductive plasma that fills galaxies can stretch, twist, and amplify even the faintest magnetic fields, strengthening them over billions of years. But this elegant mechanism only solves half the puzzle. It can magnify a field, but it cannot create one from nothing. The dynamo requires a seed, a weak initial magnetic field to get started. The source of these primordial seeds is the true mystery. Where did the first whispers of cosmic magnetism come from? Some theories point to the violent infancy of the universe. In the first fractions of a second, the cosmos may have undergone dramatic phase transitions, analogous to water freezing into ice. As the universe cooled, these shifts in the fundamental state of reality could have generated immense currents, seeding space with the first magnetic fields. Other hypotheses suggest that the same inflationary epoch that smoothed the cosmos might have also rippled it with primordial electromagnetic waves, leaving behind a faint magnetic imprint. Could these vast magnetic fields we see today be a fossil relic, a permanent scar from a more complex and dynamic early universe? Their silent, pervasive presence suggests an underlying layer of physics, a history of phase transitions or exotic fields we have not yet discovered that set the stage for everything that followed. Our most cherished laws of physics might not be universal laws at all. They could be nothing more than local ordinances, the quirky bylaws of our own cosmic hometown. This is the staggering implication of the multiverse hypothesis, a concept that radically redefines the nature of reality. The idea comes in several distinct forms, each more mind-expanding than the last. The first is the cosmological multiverse, a direct consequence of the theory of eternal inflation. In this picture, the Big Bang was not a unique event, but a single bubble nucleating in an eternally inflating background. This process never stops, constantly spawning new bubble universes, each one a self-contained cosmos with its own properties. Another version emerges directly from the quantum world. The many worlds interpretation suggests that every time a quantum event has multiple possible outcomes, the entire universe splits, creating a branching tree of parallel realities. In one branch, you turned left on your way home, while in another, equally real branch, you turned right. Every decision, every random atomic decay spawns a new universe. Then there is the mathematical multiverse, which posits that every possible mathematical structure must exist as a physical reality somewhere. The sheer variety is overwhelming, a taxonomy of existence where every conceivable set of physical laws is realized in some cosmic domain. This proliferation of worlds offers a potential solution to one of the deepest puzzles, the apparent fine-tuning of our universe for life. The fundamental constants of nature, like the strength of gravity or the mass of an electron, seem perfectly calibrated. If gravity were even slightly stronger, the universe would have collapsed back on itself long ago. If the nuclear force were marginally weaker, hydrogen would be the only element, and no complex chemistry could exist. In a single universe, this exquisite balance seems like an unbelievable coincidence, a miracle. But in a multiverse, it becomes a statistical inevitability. With an infinite number of universes, every possible combination of constants will be tried. Most of these universes will be stillborn or barren, collapsing instantly or containing only radiation. But in a tiny, fortunate fraction, the numbers will line up just right. In those rare cosmic oases, stars will ignite, planets will form, and life will eventually arise to wonder at its own existence. We do not live in a specially designed universe, this reasoning suggests. We simply live in one of the few that can support us. This is known as the Anthropic Principle. While this idea resolves the fine-tuning puzzle, it comes with a profound and humbling cost. It implies that the quest for a single, elegant theory of everything, one that uniquely predicts all the constants we see, may be fundamentally misguided. There is no deeper reason why the mass of the electron is what it is. It just is in this universe. Next door, in a neighboring bubble, it could be 1,000 times heavier. The laws we spend our lives trying to decode are not the fundamental laws of a solitary cosmos. They are merely the parochial customs of our own cosmic neighborhood. This forces us to confront a difficult question about the nature of science itself. If most of reality is permanently beyond our observational horizon, forever inaccessible to experiment or measurement, can we still call this science? The multiverse may be the ultimate expression of cosmic complexity, but it also stands as a monumental challenge, expanding the canvas of reality far beyond the limits of our perception and perhaps beyond the very reach of our understanding. The river of time flows in only one direction, from a past we can remember toward a future we cannot see. This psychological arrow of time feels absolute, an undeniable part of our existence. Yet when we look at the fundamental laws of physics, a profound contradiction emerges. The equations governing particles, from Newton's mechanics to Einstein's relativity and quantum theory, are almost entirely time-symmetric. They work just as well running forward as backward. A video of two electrons colliding and rebounding would look perfectly natural played in reverse. So why does the macroscopic universe, the world of shattered glasses and aging faces, display such a powerful and irreversible directionality? The answer appears to lie not in the fundamental laws themselves, but in the concept of entropy, as described by the second law of thermodynamics. Entropy is a measure of disorder, and the second law states that the total entropy of an isolated system always increases over time. The universe as a whole began in a state of incredibly low entropy, a highly ordered and unlikely configuration, perhaps at the moment of the Big Bang. Ever since, it has been evolving toward states of higher and higher disorder. We remember the past because it was more ordered, and we move into a future of increasing chaos. This rising tide of entropy gives us the arrow of time we experience, but this only pushes the mystery one step further. Why was the past so ordered to begin with? This is where our understanding of time itself begins to unravel. The physicist Carlo Rovelli has proposed a radical idea, suggesting that time is not a fundamental ingredient of reality. He argues that time is an emergent property, a macroscopic illusion that arises from our limited thermodynamic perspective, much like the sensation of temperature emerges from the jostling of countless molecules. At the most fundamental level, Rovelli's loop quantum gravity suggests there may be no time at all, just a network of interrelated events. This challenges the very fabric of our perception. General relativity already warped our classical view by treating time as a malleable fourth dimension, a fabric that can be stretched and curved by mass and energy. But when we try to merge gravity with quantum mechanics, the concept of time faces its greatest crisis. The equations of quantum gravity, in some formulations, simply do not include a time variable. They describe a static, timeless landscape of relationships. So if time is not fundamental, what are we actually experiencing? Our relentless march from birth to death, the ticking of every clock, might be a kind of cosmic forgetting, a result of our inability to perceive the full, timeless quantum state of the universe. Could our single, linear arrow of time be just one thread in a far richer temporal tapestry? Are there layers of time hidden from us, perhaps multiple dimensions or even closed loops, where cause and effect lose their familiar meaning? We are like flatlanders living on a two-dimensional plane, completely unaware of the vast third dimension above and below. Our consciousness may be trapped on a one-dimensional timeline, unable to perceive the true, complex architecture of temporality that underpins our reality. Two of humanity's greatest intellectual achievements stand in stark opposition to one another. On one hand, we have general relativity, Einstein's magnificent description of gravity as the elegant curvature of spacetime. It paints the cosmos on a vast canvas where planets orbit and galaxies collide in a smooth, continuous geometric dance. On the other hand, we have quantum mechanics, the bizarre and wildly successful rulebook for the subatomic world. Here, reality is grainy and probabilistic, a realm where particles pop in and out of existence and can be in two places at once. Both theories are spectacularly accurate within their own domains, yet when brought together, they produce nothing but nonsense. The force that holds our feet to the ground simply does not fit into the quantum rulebook that describes every other fundamental force. This is the central conflict driving the search for a theory of quantum gravity. How can the smooth, geometric fabric of spacetime possibly emerge from the frantic, discrete jitter of the quantum world? The two leading contenders offer radically different answers. String theory proposes that the fundamental ingredients of reality are not point-like particles, but unimaginably tiny, vibrating loops of energy. The different resonant patterns of these strings give rise to every particle and force we know. To make the mathematical symphony work, string theory requires extra dimensions of space beyond the three we experience. These dimensions are thought to be curled up into a complex, microscopic shape at every single point in our familiar space, a hidden geometry that dictates the laws of physics in our universe. Loop quantum gravity takes a more direct approach. It suggests that space itself is not smooth and continuous, but is woven from a fabric of finite, interwoven loops. In this view, space has a discrete, atomic structure. Picture a supremely fine mesh, with each individual thread a billion trillion times smaller than an atom. The area and volume of any region of space can only take on specific quantized values, much like the energy levels of an atom. Here, spacetime is not a passive stage, but a dynamic, evolving network of relationships. The profound challenge is that these theories currently exist in an experimental vacuum. The energy scales required to probe these fundamental layers of reality are far beyond the reach of any particle accelerator we could ever build. We are like architects trying to deduce the molecular structure of stone by studying the shape of a cathedral. The silence from nature is deafening, forcing us to confront a humbling possibility. The true theory of everything may not be a simple, elegant equation that fits on a T-shirt. It might require a new kind of mathematics and conceptual frameworks that we have not yet invented, pointing to a universe whose operating system is of a complexity we can barely begin to fathom. Deep in the cold silence of the outer solar system, two robotic explorers began to whisper a secret. The Pioneer 10 and 11 spacecraft, after their triumphant missions to Jupiter and Saturn, were coasting toward interstellar space. Yet as scientists tracked their trajectories with exquisite precision, they noticed something deeply puzzling. Both probes were experiencing a tiny, unaccountable deceleration, a faint but persistent drag toward the Sun. This was the Pioneer Anomaly, a minuscule drift of less than a nanometer per second squared, a deviation so small it seemed it should be negligible. But in the pristine equations of orbital mechanics, a ghost in the machine is everything. For decades, this tiny signal haunted physicists. Was it evidence of a subtle flaw in our understanding of gravity, perhaps a hint of modified Newtonian dynamics at extremely low accelerations? Or was it something entirely new, an unknown force acting across billions of miles? The mystery endured until a meticulous investigation pointed to a surprisingly mundane culprit, the gentle but constant push of heat. The spacecraft's radioactive power sources generated warmth, and when that thermal radiation bounced off the asymmetrical craft, it created a tiny photon pressure, a faint breeze that was just enough to produce the observed deceleration. The case was largely closed, yet the legacy of the Pioneer Anomaly is far more profound than its resolution. It stands as a powerful cautionary tale about the limits of our models. As one NASA engineer noted, when you are navigating a spacecraft across the solar system, a deviation of just a few meters can mean missing a planet entirely. You have to account for every possible effect, from the pressure of sunlight to the gravitational pull of distant asteroids. The fact that thermal radiation, a known force, was almost overlooked reminds us how easily we can mistake an unmodeled piece of our own technology for a revolution in physics. But what if the next anomaly is not so easily explained? Other spacecraft, like the Galileo probe on its mission to Jupiter, have shown their own tiny, unmodeled accelerations. Are these just statistical fluctuations, the background noise of a complex solar system? Or could they be the faint whispers of something deeper, a subtle modification to gravity or a hint of an unknown interaction with the invisible sea of dark matter that we know permeates our galaxy? These minuscule signals challenge the very completeness of our gravitational models. We have mapped the grand curvature of spacetime with general relativity, yet these tiny, persistent tugs suggest that our map, for all its beauty, might still be missing some of the finest details, subtle components of physical law that only reveal themselves in the vast, quiet emptiness between the stars. The oldest light in the universe carries a message from its very first dawn. This is the cosmic microwave background, a faint afterglow that permeates all of space, a snapshot of the cosmos when it was just 380,000 years old. Before this moment, the universe was a hot, dense fog of plasma, where light was constantly scattered by free electrons. As everything expanded and cooled, those electrons combined with protons to form the first neutral atoms, and the universe suddenly became transparent. That first burst of light, stretched and cooled by 14 billion years of expansion, now reaches us as a uniform microwave whisper, just a few degrees above absolute zero. This cosmic fossil is our Rosetta Stone for decoding the universe's infancy. By mapping its minute temperature fluctuations with incredible precision, satellites like Planck have confirmed the broad strokes of our cosmic story. The tiny hot and cold spots in this background radiation are the seeds of all future structure, the quantum ripples stretched to cosmic proportions by inflation, destined to become galaxies and clusters. Yet for all this success, the cosmic microwave background holds stubborn mysteries. The most famous is a bizarre statistical quirk nicknamed the axis of evil. According to the foundational cosmological principle, the universe should be isotropic, meaning it should look roughly the same in every direction on the largest scales. The temperature fluctuations in the afterglow should be randomly scattered like a static hiss, but they are not. There is a strange, unexpected alignment of some of the largest features in the sky, a preferred direction that seems to hint at a fundamental asymmetry in the cosmos. It is as if the universe has a faint, ghostly fingerprint, a subtle grain to its fabric that should not be there. Could this just be a statistical fluke, a cosmic mirage that will vanish with more data, or is it a genuine crack in our standard model, a clue to a deeper truth? One possibility is that it is an echo from a time before inflation, a scar from the universe's very first moments when its geometry was not yet set. Another, even more mind-bending idea is that the universe has a non-trivial topology. We naturally assume space is infinite and flat, like an endless sheet of paper. But what if it is finite and connected, like the surface of a vast, multidimensional donut? In such a universe, if you traveled far enough in one direction, you would eventually return to your starting point. Light would wrap around this structure, and the patterns we see in the cosmic microwave background could be multiple, overlapping images of the same ancient structures, creating the illusion of alignment. The pristine data from the afterglow, our most powerful probe of the beginning, is telling us that the initial conditions were likely shaped by forces and fields far more exotic than our simple inflationary paradigm allows. The universe's opening act may have been a drama of incredible complexity, and we are only just beginning to read its opening lines. A brilliant flash of energy brighter than 500 million suns vanishes in less than a blink. This is the fast radio burst, one of the most violent and puzzling phenomena in the modern cosmos. These millisecond-long pulses of radio waves arrive from galaxies billions of light-years away, carrying more energy than our Sun emits in 80 years, all compressed into a fleeting instant. As one astronomer from the CHIME collaboration put it, pinpointing their origin is like trying to find a specific grain of sand on a planet-wide beach with a single, incredibly brief camera flash. The mystery deepened when we discovered that some of these bursts are repeaters. They flash again and again from the same patch of sky, ruling out cataclysmic, one-time events as the sole explanation. One major breakthrough came when scientists traced a repeating burst back to a magnetar, an intensely magnetic neutron star within our own galactic neighborhood. This provided a crucial clue, suggesting that at least some FRBs are born from the immense, twisted magnetic fields of these cosmic powerhouses, yet this solved only one piece of the puzzle. The overwhelming majority of fast radio bursts are one-off events, singular explosions from the deep universe with no subsequent encore. What cosmic process can unleash such staggering power so abruptly and then simply vanish? The theories are as varied as they are extraordinary. Some point to the epic collision of two neutron stars, a merger so violent it warps spacetime itself. Others suggest the sudden, star-quaking rupture on the surface of a highly magnetized neutron star, an event known as a magnetar flare. More exotic ideas venture into the realm of cosmic strings, hypothetical defects in the fabric of spacetime left over from the Big Bang, vibrating and snapping to release unimaginable energy. And of course, there is the more speculative notion that these could be signatures of advanced civilizations, perhaps powering interstellar light sails with focused radio beams so powerful they briefly outshine entire galaxies. But could the true answer be even stranger? Could fast radio bursts be a manifestation of physics operating in environments so extreme we have not yet conceived of them? Imagine new states of matter like strange matter or superconducting fluids deep within neutron stars undergoing a phase transition and releasing a shock wave of energy. Or consider a new mechanism for energy release, a fundamental process that only occurs under gravitational forces and magnetic fields a quadrillion times stronger than any we can create on Earth. Their brief, overpowering nature is a direct message from the most extreme laboratories the universe can build. They hint at physical processes operating on scales and under conditions that lie entirely outside the bounds of our current theories, a stark reminder that the cosmos still holds phenomena for which we have no name. The smooth, continuous flow of a river emerges from the chaotic dance of countless water molecules. Not a single molecule is wet, not one possesses the property of fluidity, yet together they give rise to the powerful, cohesive force of a current. This is the essence of emergence, where complex behaviors and properties arise from the collective interaction of simpler parts. Now apply this logic to the very fabric of reality. If spacetime is not fundamental, then what we perceive as the smooth, curving stage of the universe and the force of gravity that warps it might themselves be emergent phenomena. They could be the large-scale consequence of unimaginably vast numbers of more basic components interacting. Picture the frantic, random motion of air molecules in a room. Individually, they are just particles bouncing around, but collectively, they create a stable, uniform pressure. In a similar way, the placid geometry of empty space and the gentle pull of gravity we experience might be the thermodynamic average of a hidden, frenetic quantum reality. This shifts our perspective from the universe as a container to the universe as a process, a dynamic computation. The most compelling evidence for this radical idea comes from a profound theoretical discovery known as the AD-SCFT correspondence. This is a concrete, mathematical realization of the holographic principle. It demonstrates a complete duality, a perfect equivalence between two seemingly different worlds. On one side, you have a theory of gravity, including strings and black holes, operating within a particular warped volume of space. On the other side, you have a quantum field theory, describing particles and forces without any gravity at all, living on the lower dimensional boundary that encloses that volume. These are not two different theories describing the same thing. They are the same theory. Every single event, every particle collision, every gravitational wave inside the volume is perfectly encoded as information and interaction on the bounding surface. It is as if the entire rich, three-dimensional movie of our universe, with its stars, planets, and people, is being projected from a two-dimensional quantum code written on the cosmic horizon. This duality suggests that gravity is not a fundamental force in the way we thought. It is not a primary ingredient in the universe's recipe. Instead, it is a side effect, a consequence of the way quantum information on the boundary is entangled and organized. Think of it like the sensation of temperature. You cannot point to a single atom and ask for its temperature. Temperature is not a property of the individual, it is a property of the collective. In the same way, gravity may not be a property of the fundamental building blocks of reality. It emerges when a vast number of those blocks are woven together in a specific holographic pattern. This leads to a staggering conclusion. The true, fundamental description of the cosmos may operate in a realm that has no space and no time as we understand them. The bedrock of reality could be a network of pure information, of quantum bits and their relationships, existing in a state beyond geometry. Our experience of falling apples, orbiting planets, and the relentless flow of time would then be a magnificent collective illusion, a user interface projected from a hidden, spaceless, timeless code. This adds a layer of hidden complexity so deep it redefines the very nature of existence, suggesting that the universe we perceive is just the emergent surface of an infinitely stranger and more abstract ocean. The universe's first 3 minutes were a forge of unimaginable power, cooking up the primordial elements that would later build stars and planets. Our models of this brief epoch, known as Big Bang nucleosynthesis, are spectacularly successful. They predicted the cosmic abundance of hydrogen and helium with stunning accuracy, a triumph that stands as one of the strongest pillars of evidence for the Big Bang itself. Yet this pristine success is marred by a single, stubborn anomaly involving the third lightest element. As one nuclear astrophysicist framed it, we have a lithium problem. The models calculate that a specific isotope, lithium-7, should be about 3 times more abundant in the oldest stars than what we actually observe. We see this discrepancy in the atmospheres of ancient stellar relics, time capsules that preserve the chemical makeup of the early cosmos. These stars contain only about 1/3 of the lithium that our equations insist should have been produced. How could our theory be so precisely right for 2 elements and so clearly wrong for a third? This is not a minor accounting error. It is a fundamental crack in our understanding of the universe's first nuclear furnace. Physicists have proposed several fascinating solutions, each pointing to a more complex infancy for the cosmos. perhaps there are unknown nuclear reactions at play. The cross-sections, which measure the probability of particles interacting for certain rare processes in the primordial soup, might be different than our laboratory measurements suggest. A slight tweak to one of these rates could destroy just enough lithium to match the observations. Other theories venture into more exotic territory. Could hypothetical particles from the dark sector have decayed in those first few minutes, altering the delicate balance of protons and neutrons and suppressing lithium production? Or, even more radically, what if the fundamental constants of nature, like the strength of the gravitational force or the fine structure constant, were not truly constant during this explosive initial phase? A universe where the laws of physics were subtly different for just a fleeting moment would leave a permanent imprint on the elemental abundances we see today. The cosmological lithium problem is a quiet but persistent alarm. It tells us that the story of the universe's birth, for all its predictive power, may have a missing chapter. The physics of the first few minutes might contain layers of complexity we have only just begun to suspect. Our existence is a single point of data that speaks volumes about the cosmos. The universe appears to be exquisitely balanced on a knife's edge, with its fundamental constants precisely tuned to allow for stars, planets, and life itself. If the force of gravity were even slightly stronger, the universe would have collapsed back on itself in a catastrophic crunch soon after the Big Bang. If the nuclear force were marginally weaker, protons and neutrons would never have bonded, leaving the cosmos with nothing but hydrogen. The mass of the electron, the charge of the proton, the energy in the vacuum of space, each of these values seems set within an incredibly narrow window that permits complexity and consciousness to arise. This is the puzzle of fine-tuning, and it leads us directly to the Anthropic Principle. This is the simple yet profound idea that the universe we observe must be compatible with the existence of observers. The weak version of this principle acts as a cosmic selection effect. We should not be surprised to find ourselves in a universe capable of supporting us, because in a universe that was not, we would not be here to ask the question. It is like a fish marveling at how perfectly water is suited to its gills. The water was not designed for the fish evolved to live in the water. The weak Anthropic Principle is a logical truism, but it opens the door to a far more controversial idea, the strong Anthropic Principle. This version suggests that the universe must have properties that inevitably lead to the emergence of conscious life. For some, this implies a form of teleology, a purpose, or even a designer behind the cosmic curtain. The debate between these two interpretations forces a deep philosophical question. Are the laws of physics necessary, written into the fabric of logic itself, or are they contingent, merely one possible set of rules among countless others? The multiverse offers a powerful, naturalistic answer to this riddle. If eternal inflation or quantum branching creates an infinite ensemble of universes, a vast cosmic landscape where every possible set of physical laws is realized, then fine-tuning is no longer a miracle. It becomes a statistical inevitability. In the overwhelming majority of these universes, the constants are wrong. Gravity is too strong, particles are too heavy, and the cosmos remains dark, empty, or stillborn. But in a rare, fortunate few, the numbers line up just right. We do not live in a special universe, we simply live in one of the habitable ones. Our cosmic home is not a unique masterpiece, but a single, complex instance in an infinite gallery of possibilities. This realization does not make our universe any less wondrous, but it does reframe our search for its ultimate laws. We are not mapping the one and only reality. We are merely deciphering the local bylaws of our own peculiar cosmic neighborhood. The quietest place in the universe is not truly quiet at all. Even in the deepest, most perfect vacuum, space itself is a seething, turbulent sea. Quantum mechanics tells us that so-called empty space is filled with a frenzy of virtual particles, flickering in and out of existence in a relentless dance. This is the zero-point energy of the vacuum, a background hum of infinite potential woven into the fabric of reality. Yet this beautiful idea leads directly to one of the most embarrassing failures in all of science, a problem so severe it is known as the vacuum catastrophe. When we try to calculate the energy density of this quantum vacuum using our established theories, we get a number of such staggering magnitude it defies comprehension. Then we look out at the cosmos and measure the actual energy density of empty space, which we call dark energy. The two values should be the same thing, but they are not even close. The theoretical prediction is 10 to the power of 120 times larger than the observed value. That is a number with 120 zeros after it, a discrepancy so vast it is the single worst prediction in the history of physics. As the physicist Lawrence Krauss has pointed out, this is not just a problem, it is a profound crisis. If our quantum field theory were correct, the repulsive force generated by this vacuum energy would have been so immense it would have ripped every atom, every star, and every galaxy apart in the earliest moments of the universe. Reality as we know it would have been impossible. So why is the cosmos so serene? Why is the actual energy of the vacuum so infinitesimally small, yet not quite zero? This colossal mismatch suggests we are fundamentally misunderstanding how gravity interacts with the quantum world. Perhaps gravity simply does not see or respond to this zero-point energy in the way our equations assume. Or maybe there exists a hidden symmetry, a delicate cancellation mechanism in nature that perfectly neutralizes almost all of this frantic quantum activity, leaving behind only the faintest whisper we detect as dark energy. The vacuum catastrophe is more than a numerical error. It is a screaming alarm that our two most powerful descriptions of reality, quantum field theory and general relativity, are telling us two completely different stories about the nature of nothingness itself. Solving this riddle will not require a small adjustment, but a revolution in our thinking, one that forces us to confront what truly lies between the stars and within the void. Einstein spent the last 30 years of his life chasing a ghost, a single, unified theory that would weave together gravity and electromagnetism into one elegant tapestry. He called it a unified field theory, and he believed such a framework would reveal the mind of God. He failed, but his dream did not die. It evolved into the modern quest for a theory of everything, a single mathematical engine capable of describing every force and particle in the cosmos, from the gravity that binds galaxies to the quantum glue holding atoms together. This is the holy grail of physics, a set of equations so profound they would encapsulate the entire universe. The two great contenders in this race, string theory and loop quantum gravity, represent vastly different approaches to this monumental problem. String theory replaces the idea of point-like particles with tiny, vibrating loops, suggesting that the different notes in this cosmic symphony produce every particle we see. But to make the music work, the theory requires extra dimensions of space, curled up into shapes so small we can never perceive them. Loop quantum gravity takes a different path, proposing that space itself is not smooth and continuous, but woven from discrete, indivisible threads, a billion trillion times smaller than an atom. Both are breathtakingly ambitious, yet both face the same, seemingly insurmountable wall. The energy required to directly test their predictions is beyond astronomical. To probe these fundamental scales, we would need a particle accelerator larger than our entire solar system. we are left with mathematics as our only guide, navigating a labyrinth of such complexity that only a handful of minds on Earth can truly follow its path. This search forces a profound philosophical question. For centuries, physicists have been guided by a faith in nature's inherent simplicity and elegance. We assume that behind the apparent chaos of the universe lies a beautiful, symmetrical, and ultimately simple set of rules. A successful theory of everything would be the ultimate validation of that belief, revealing that all complexity, from the birth of stars to the spark of consciousness, emerges from a concise and powerful source code. But what if our aesthetic sense is lying to us? What if the universe is not simple, and our cherished concepts of elegance and beauty are merely human preferences, like preferring a classic sonata to the chaotic noise of a storm? The sheer, grinding difficulty of this quest, the decades of dead ends, and the mathematical monstrosities we encounter might be trying to tell us something crucial. The fundamental architecture of reality may be inherently, irreducibly complex. There may be no single, simple equation at the bottom of it all, only an endless cascade of intricate structure, a cosmic onion with an infinite number of layers. The search for a final theory, then, becomes more than a scientific endeavor. It is a mirror, reflecting the depths of our own ignorance and challenging the very way we think about the cosmos. An intricate cosmic web of galaxies stretches across the void, a tapestry of filaments and vast, empty bubbles. Yet for all its apparent complexity, this grand structure holds a profound secret, a hidden order that emerges only when we step back to see the biggest picture. The distribution of galaxies, clusters, and superclusters is not random chaos. It follows a remarkably simple statistical pattern known as a power law distribution, a rule where the number of large structures decreases in a precise, predictable way as you look at smaller and smaller scales. This property, called scale invariance, means the universe looks statistically similar whether you're surveying a region a billion light-years across or one that is merely 100 million. This elegant pattern is a direct echo of the universe's first moments. It emerges from the initial Gaussian fluctuations, the quantum seeds imprinted during inflation, which were almost perfectly random and smooth. As the cosmologist James Peebles noted, the large-scale simplicity of the cosmos is a triumphant prediction of our standard cosmological model, a beautiful confirmation that we are on the right track. Yet this very success presents a deep puzzle of its own. Why should a system with so many degrees of freedom, shaped by billions of years of violent, nonlinear gravitational collapse, mergers, and feedback from supernova and black holes, result in such a clean and simple statistical pattern? It is like expecting a forest, after eons of growth, storms, and fires, to arrange its trees according to a single, straightforward mathematical rule. This unexpected simplicity could be a profound clue that the underlying physics governing cosmic structure is far more constrained and elegant than we have dared to imagine. The tumultuous history of galaxy formation may be channeled by fundamental principles that force the final product into a statistically uniform shape. Or this clean pattern might be a beautiful mask concealing a deeper level of complexity that only our next generation of telescopes, peering into the dark matter backbone of the cosmos with unprecedented precision, will finally reveal. Our most successful scientific theories are not perfect mirrors of reality, but merely maps of a territory we can never fully explore. This is the unsettling challenge to scientific realism, the philosophical stance that our theories provide a true and accurate description of the world as it really is. If the universe is 10 times more complex than our best models suggest, then what we call reality is just a useful approximation, a simplified user interface that allows our minds to navigate a cosmos whose true depths are permanently hidden. The philosopher of science Thomas Kuhn profoundly reshaped our understanding of this process. He argued that science does not progress in a smooth, linear march toward truth. Instead, it lurches forward through revolutionary paradigm shifts, where an old framework for understanding the world collapses under the weight of its own anomalies, and a new, incommensurable one takes its place. The universe did not change when we moved from Newton's clockwork to Einstein's relativity, but our entire conception of space, time, and gravity was utterly transformed. We are likely living through such a shift right now, surrounded by the anomalies of dark matter, dark energy, and the vacuum catastrophe, all pointing toward a new paradigm we cannot yet fully see. This leads to a humbling possibility. The human mind is not a universal reasoning engine. It evolved on a single, sheltered planet to solve practical problems of survival, to recognize patterns in the rustling grass and track the movements of prey. Our cognition is built for navigating a middle world of medium-sized objects moving at modest speeds. Is it any wonder that we find the probabilistic weirdness of the quantum realm or the 11-dimensional landscapes of string theory so deeply counterintuitive? We are like flatlanders trying to comprehend a sphere, our senses and our very logic constrained by the dimensions of our native home. This does not mean that science is a futile endeavor. Far from it, the power of the scientific method is that it allows us to transcend our innate limitations, to build tools and create mathematics that let us peer into the shadows. But it does suggest that our journey of discovery is infinite. Every answer we uncover does not lead to a final, elegant equation at the end of the road. Instead, it opens a door to a room filled with 10 new, more intricate questions. The cosmos may not just be stranger than we imagine, but stranger than we can imagine. Our purpose, then, may not be to solve the universe, but to endlessly explore it, finding ever deeper layers of meaning and connection in an existence whose ultimate complexity may forever lie just beyond the horizon of our understanding. The journey through these cosmic mysteries reveals a pattern far deeper than any single anomaly. Dark matter's ghostly pull, dark energy's relentless push, the quantum enigma of information, and the staggering possibility of a multiverse are not isolated puzzles. They are interconnected clues, each one a single thread in a tapestry of reality that is orders of magnitude more complex than our current maps suggest. The universe is not just a little more complicated than we thought. It appears to be fundamentally, overwhelmingly more intricate, with entire layers of physics and existence still waiting to be uncovered. This is not a cause for despair, but an invitation to remain endlessly curious and open-minded. The cosmos is the greatest story ever told, and with every discovery, we realize we have only just turned the first page. We would love to hear which of these mysteries captures your imagination the most. Share your thoughts in the comments below, and subscribe to continue this incredible journey of discovery with us.